And hello, let's continue where we left off. So over here, we just spent the last video trying to explain how we got ourselves at this equation such that we have this buoyancy force term. Rho infinity minus rho bracket times g. So this term here talks about the change in density between rho infinity in the free stream and of course in the boundary layer, the density in the boundary layer, which is rho. Okay, so how do we quantify this? Because this term here, it's not it's we sort of know it's related to temperature, but we haven't explicitly stated the form. Okay, so the simplest assumption we can make is something called the Boussinesq approximation. Okay, the Boussinesq approximation. Okay, so the Boussinesq approximation, where is it? A Boussinesq approximation is basically saying that density sort of, or the percentage change in density, percentage change in density varies linearly with temperature. Okay, percentage change in density varies linearly with temperature, so to speak. And not just that, the density change is very, very small. Okay, so this is it. Okay, this constant. Yeah. So this is the Boussinesq approximation, where rho is equals to rho infinity 1 minus beta t minus t infinity. Okay, so this is from Bijan's textbook. So there's a linear relationship between the density and the fluid temperature. That's all that this equation is telling us. So it's a linear relationship. Okay, it's a linear relationship. It's, again, not very what do you call that? Not too complex. And if you remember what rho infinity, beta was, okay, beta equals to minus 1 over rho d rho dt at constant pressure. So it's the fractional change in density when you change the temperature only. Okay, so it's the rate of change of density. The fractional rate of change of density with respect to temperature at constant pressure. Okay, so of course you can use this to see where this expression comes from. Okay, this is the definition of beta. Okay, and if we assume a linear, so-called a linear relationship of density and temperature, this is what will come about. Okay. Okay, so I will leave it as that. But the thing is that we will want to substitute this expression for rho into here. So that while we're doing this, we want to see the explicit relationship between the buoyancy force term, which is rho infinity minus rho g. This is the net buoyancy force term. And we want to see it explicitly depend on temperature. So if we were to substitute this rho into here, we will just get this term, okay? We will just cancel off some ones and everything, which I'm not interested to show. But we'll get this, okay? The buoyancy force term on the right will be rho infinity beta t minus t infinity times g. Okay, once again, rho infinity beta t minus t infinity times g. Okay. Once again, for the sake of simplification, we can also say that the difference in density between the rho infinity and rho is very small. Okay, so that we can just divide throughout by the density. Okay, once again, for sake of simplification, density changes here are not important except that the buoyancy forces are accounted for. So the only place where we care about change in density is in this buoyancy force term. Everywhere else, I don't really want to care about, this change in density. Okay, again, it's the same logic as why we still use the incompressible form of the Navier-Stokes equation for this natural convection case. We only account for the buoyancy force terms for change of density. Every other term is not affected. Okay, it's basically semi-incompressible in that regard. Or maybe the right term is quasi, but it's a very complicated term. Okay, so end up the y momentum equation will look like that: u du dx v dv dy minus nu blah blah blah. This is the viscous force term. It will be balanced out with the buoyancy force term. So these two terms contribute to advection, or they are advection terms. These are viscous force terms, and this here is the buoyancy force term. Okay, so now we have that. What's our custom, so to speak? Our custom with boundary layer equations is to take out unnecessary terms to make life easier for ourselves. So how do we take out unnecessary terms? Okay, remember we start by non-dimensionalizing. Okay, non-dimensionalizing with the correct scales. Okay, so let's start with continuity equation. Okay, we can start with the continuity equation. Let's see here. Cause mass balance is usually where we will first start. Okay, so we have a du dx plus dv dy equals to 0. Simple enough. X equals to x star. X star is a dimensionless distance on the order of magnitude of 1. Okay, remember all the dimensionless quantities, they are on the order of magnitude of 1. That's how we want to perform our scaling analysis. So we cannot just use any old length we want. We need to make sure that x star is on the order of magnitude of 1. Okay, so how do we make sure that is the case? We use the appropriate scaling term for this dx. Okay, the appropriate scaling term will be delta t. Right, this is the thermal boundary layer thickness. Okay, so within the boundary layer here, x only goes from 0 to delta t. So you don't expect any bigger change than that, right? Inside boundary layer. So these are equations describing motion and flow within the boundary layer. Okay, in this case it's the thermal boundary layer, which I like, the thermal boundary layer thickness which I'd like to use. Momentum boundary layer thickness, that depends actually. Okay, if your Prandtl number is very big, chances are your momentum boundary layer thickness is going to be much greater than the thermal boundary layer thickness, because of the way momentum diffuses faster than temperature. But that's we may talk about that again later on. Okay, so we see that the length scale of x is determined by this thermal boundary layer thickness. Y is determined by h, where h is wherever you want h to be. Okay, they are your point of reference. Okay, if this is y equals to 0, this is y equals to h. Okay, so if we are y equals to y, this length h is what we will use to non-dimensionalize our y coordinate. Similar to the forced convection boundary layer. Okay, problem is this: unlike the forced convection, normally we will have a free stream velocity. Okay, but for the boundary natural convection boundary layer equations, the free stream velocity for u and v are both 0. Okay, or close to 0, as I was explaining before. It's pretty much 0. So you don't really have a u infinity to look to here, right? So how can we continue on? Okay, so we are basically stuck when we do with the continuity equation, because we don't know what the characteristic velocity scales are just by looking at this. So where do we find the characteristic velocity scales? We need to start looking at where what's the driving force behind, you know, these velocities, which is the energy, the transport of heat energy. So maybe it's easier to start by looking at our energy equations, right? Because that's the driving force behind the natural convection. So we'll start by looking at the energy equations first. So this is our energy equation. Here are the advection terms here. U del T del X, V del T del Y equals to alpha. Then we have the Laplacian term of temperature, which accounts for conduction. So advection equals to conduction. Nothing more, no heat source, no nothing else. Okay. So I'm going to use the same way of delta T and H. Okay, you're going to use delta T and H to non-dimensionalize X and Y. So that's what I have done here. So delta T, then you have del X star, H del Y star, and then all of these are non-dimensionalized. All of the length scales are non-dimensionalized. So X, Y, X square, Y square, they are non-dimensionalized in the following manner. Okay, next obvious thing for us is to non-dimensionalize T. Okay, what's the standard way we non-dimensionalize T? Okay, so we like to talk not in terms of absolute temperature, but the temperature differences. So just like in the forced convection, we like to compare the surface temperature with the fluid temperature. So Ts minus T infinity, that will be the non-dimensional. That will be what we use to scale our temperature, such that this theta, non-dimensional temperature, is on the order of magnitude of 1. So this will be on the order of magnitude of 1. So if you want to replace this dt, okay, we will need this term here, dt minus T infinity, because dt minus T infinity is basically just what dt is, right? Because T infinity is constant, it'll just disappear. Okay, so dt minus T infinity is equals to Ts minus T infinity d theta. So I just took different derivatives of both sides and I shifted Ts minus T infinity to the left hand side. That's all. And I added an extra dt here just for your reference. Okay. So we'll want to substitute all dt for this d theta Ts minus T infinity. So how are we going to do that? Okay, we'll just substitute. Everywhere we see dt here, we'll just put it in. Okay, so first what I do, okay, we'll start with the same equation we left off. I will add the minus T infinity to this dt here. Okay, I'll add all of them here. And then I'll substitute dt minus T infinity equals to d theta Ts minus T infinity. So I have d theta, d2 theta, and d2 theta. And all the Ts minus T infinity gets pulled out into the equation, or rather the coefficients in front. Okay, not too bad, not too bad. So before we continue, we start to see a little bit of a way we can, knock off one of the terms. So we see on the right hand side in the Laplacian, okay, the conduction terms, alpha, and then you have this term in the brackets here. Okay, so alpha times this factor, this thermal temperature gradient factor. Okay, is it possible to lop off one of these terms, to just take off one of these terms? And answer is yes. Why? Because when you add these two together, okay, you will note, when you consider these two terms, this d by dy, okay, this temperature gradient in the y direction, or the second order derivative of the temperature in the y direction, or it is this term here is on the order of magnitude of 1, same as this term here. However, the coefficient in front has a 1 over h square here, and this thing here is actually delta t squared. We know that h is actually much bigger than the thermal boundary layer thickness at any point in the fluid. Okay, so for a fixed h, if you were to fix this this height y of the wall, the height of the wall, okay, the thermal boundary layer thickness is much smaller than this h. Okay, so what I'm doing here is to take these two terms and I'll approximate it as just the first term. Okay, so this del by del 2 by del x squared term plus del 2 by del y squared term. Okay, of course these are non-dimensionalized versions of those. Okay, these two terms added together will be approximately just the first term because the second term can be neglected because h is much bigger than delta t. So we can actually simplify our first term. Okay, our first term is over here. All right. So remember, I want to emphasize again and again, all the non-dimensional terms are on the order of magnitude of 1. Okay. So the order of magnitude of this and the order of magnitude of this, okay, you add them together, of course, you'll have the order of magnitude of this term here. Okay, all the rest of these are on the order of magnitude of 1. Okay, so how can we then continue? Okay, we have a u delta t, u over delta t, v over delta h. Okay, so this gives us one more equation we can sort of use to think about. Okay, I have not non-dimensionalized u and v because we have not talked about the relationship between u and v. How do we find relationship between u and v? We have to go back to our continuity equation. So we still need to come back to our continuity equation to find the relative relationship between u and v. So I'm going to non-dimensionalize our continuity equation now. Okay. So when I non-dimensionalize it, this is what will happen. Okay. When I non-dimensionalize it, this is what will happen. I will just use this term loosely, the order of magnitude of u. I will just use that to non-dimensionalize u. So that, I mean, this is a kind of a trivial statement, but let me just write it out for clarity. Okay, u equals to mathcal O, order of magnitude of u times u star. Okay, we are now figuring out the velocity scales of the x velocity or y velocity, but I just use them as placeholders for the time being. Okay, so I do this for the x velocity and I'll do the same for the y velocity. I won't write it down here, but the idea is more or less the same. They are just placeholders. Okay, so what do I then get? Okay, I get two terms on the order of magnitude of 1, and what I will get is the order of magnitude of u over delta t is equals to the order of magnitude of v, the y velocity over h. Okay, this is from the continuity equation. So if both things here are on the order of magnitude of 1, the order of magnitude of this term here and the order of magnitude of this term here must be the same. Okay. With this in mind, we can sort of substitute something into our energy equation, and we can work from there. Okay. Let's see how much time we have left. Okay, let me finish this part and we'll talk about the rest. Alright, so this is good news because this u over delta t is equals to v over h in terms of order of magnitude. So you can see here u over delta t, v over h. So what does it tell you? Basically, I can just replace this because we are talking about order of magnitude here. It's not exact. We can just replace this u over delta t with v over h. Okay, so basically that's what I'm doing here. 2 order of magnitude of u. Okay, that's if I just eliminate if I eliminate v over h using this substitution, I will get 2 times the order of magnitude of u over delta t equals to all of these terms here, alpha over delta t squared. So actually I can just get rid of this ts minus t infinity here. Okay, so which I will just do it here. Let me get rid of the ts minus t infinity. Okay. Okay, so this is the equation we are playing with. So after getting rid of the ts minus t infinity, we will get this equation here. Maybe I'll make it look a bit nicer. Alright, so we have this equation here. So since we have this from the continuity equation, we can swap out the v over h. So we have 2 times okay, 2 times this okay, we have 2 times of this, 2 times of u over delta t equals to alpha over delta t squared. Alright, so basically if I shift the delta t to the other side, I will have this equation here. Now if I swap around and I replace okay, if I eliminate u, okay, using the same method, if I eliminate the x velocity using the same method, then I will get this term here. So not too much of a problem, I hope. Okay, so wrong place. Yeah, if I eliminate this u velocity, I will get just this 2 times the order of magnitude of v. Of course, I bring the h over. I'll bring the h over. That's why I have the alpha h over here. Okay. So now we have our velocity scales. Okay, determined by all of these. The alpha, which is the thermal diffusivity, the height, of course the boundary layer thickness. Okay, not too much of a hassle there. At least we find some velocity scale and it's related to the heat transport, which makes sense. Okay, of course we can also get rid of the factor of 2. You will see in most textbooks we don't include this factor of 2 here. Because 2 is on the order of magnitude of 1. I mean, you can argue this. Okay? 2 is on the order of magnitude of 1. I mean, it's 1 times 2 is 2. Okay. But yeah, so yeah, it's on that order of magnitude. Okay. So I mean, you can use this argument, and then you will just get these two final forms here. Your velocity scales for x direction is alpha over delta t. Your velocity scale in the velocity scale in x direction, alpha over delta t. Velocity scale in the y direction, alpha h over delta t squared. Okay. So now at least you have, based on your not momentum yet, based on your energy equation and based on your mass balance equation or continuity equation, we have come up with these conclusions here. Suitable velocity scales for x and y direction. Okay, so next time we'll probably look at the momentum equations because we have all the right scales that we need. Okay, but I will not do that in this video lest it goes too long. Okay, so I'll just stop now and say thanks for watching. See you again.